Alright, now that we have the displacements for this particular linear elastic static problem, we can go on and compute the strains and stresses. In order to do this, we will first look at one element. What I did here was I set the created variable IEL, set it to 1 because I want to extract the nodes from the first element, and this is how I do that. So nodes contains the nodes of all the elements. So every element is in a row, so I'm getting the first row here. So this means grab this row, which is the first row, and all the columns. So I node is now containing these nodes. Then I know that P contains my coordinates, and these nodes are referencing the rows in these points. So I node is referencing the 441st row of P, and so on and so on. So IP now contains my 3 points that make up the first element. In the same way, U, which we created earlier in the last session, contains all of the displacements divided into the first column, which contains the x displacements, and the second column, which contains the y displacements. So IU now contains all the displacements for this particular element. Then I'm taking the magnitude or the resulting displacement here, and I want to plot this. So I want to plot the first element. So basically I'm doing the patch function here. So I'm writing phases, and I have the first element. The local coordinates are just going to be 1, 2, 3, and the vertices are contained in IP. And I set the face color to white. So this is my first element here in my coordinate system. And then I also set text, so I'm writing these text boxes here to show that these coordinates here are indeed these node numbers. Alright, so far so good. So we have a visualization of this small element. Next thing, we are going to displace it by this amount, IU, and we're going to scale up the displacements to get the representation of what we have here. So we're doing another patch here, but now the vertices are IP plus IU times some scale here. I'm setting the face color to cyan, the face alpha to 0.5, but then also I'm changing the line style to get the dashed line style like this, and then I'm setting the color data to IUR because I want this to be interpolated, so face color interpolator. So what I want to do now is I want to compute the strain. Everything starts with the strain, and then we can compute the stresses from there. So you can follow the lecture notes, but basically this is it. So you have the strain definition here for small strain elasticity, and this basically means 1/2 the gradient of U transposed plus the gradient of U. So the gradient of U is this, and this we approximate using our basis functions, the derivative of our basis functions, which you need to calculate. And this is done by using B here, because this stuff here for all of them are results in this B matrix. And for our linear triangle, it just becomes this here. Alright, so our displacements for a linear triangle we have already seen here. These are our displacements here. It's a matrix, a 3x2 matrix, and the gradient of this is taking this B, which contains the derivatives of basis functions, times the displacements. Alright, but how about B? We don't have B. Well, B, we need to calculate the Jacobian and multiply its inverse by B hat. Alright, so what is B hat? Well, B hat is just the basis functions for our linear triangle here. And these we have because they are linear, so they become constant when we take the derivative of them. Okay, and the Jacobian is b hat times the points, and the points we already have as well. So our points are here. Great. Now we can begin doing this. So we have our b hat equal to, and we have -1, 1, 0, and -1, 0, and 1. That's our b hat. And we have our IP, so we're gonna write that the Jacobian is equal to b hat times IP, and this is our Jacobian here. Usually you do this by hand, and it's quite straightforward. So another thing I want to point out is we are computing these strains when we do this per Gauss point or per integration point. So we are actually evaluating these functions here somewhere, and it should be obvious if you're looking at this now that you cannot evaluate these in some points. They are constant, and that's quite right. What we're doing now is the easiest case, where we don't have any Gauss points. We just evaluate this in the midpoint, and this is nice and easy because everything just becomes straightforward. You don't need to think about it. The thinking comes when we choose a quadratic basis function where we in fact have Gauss points and we need to compute them. And in another case, when we need to think about having several integration points, is when we are doing the when we are computing the mass matrix later on, when we will do the averaging of the nodal values in order to get the nodal values. So we'll come back to that. But for now, this is easily followable by hand, so please do that. So we have the Jacobian next. Once you have the Jacobian, we can get the B matrix by doing this. So what you could do is, take the inverse of the Jacobian, so you can check, because you would probably do this when you do it by hand. So you can here go ahead, check that this is correct. But when you do this in Matlab, what you will be doing is actually saying, alright, we have B, and this is J \B hat, because this will generate the same, and this is much more efficient than doing this inverse of J times B hat. In fact, this is so bad to do that Matlab actually warns us. In A times B can be slower and less accurate than A \B. Consider using A \B for inverse A times B, or B /A for B times inverse A. So yeah, so now you know that. Another way of writing this could be J to the power of -1. This also works, but this is also a slower method. The absolute best thing to do is to go ahead and do this. Yeah, so I'm gonna leave you with the best practice. Okay, so we have B now. So again, B means that we have the basis functions, the derivatives of the basis functions with respect to x here. So this is the first basis function with respect to x, this is the second basis function with respect to x, and this is the third, and so on for this here, but with respect to y. Alright, so we have B. Now we can take the gradient of u by multiplying B with IU, and this is our gradient of u. So we can type grad u here. So we have that as a variable. And finally, our strain is 1/2 grad U transpose plus grad U. So epsilon is equal to 1/2 times parentheses grad U transpose times grad U, or not times but plus. So there's our strain. Good. So once we have the strain, you can see here we have a matrix. So this is the strain in the x direction, the strain in the y direction, and then we have a shear strain here, and this is indeed symmetric. The symmetry comes from that we have grad U plus grad U here, and then 1/2 of that. So that's why this is, every matrix will be symmetric if you do this to it. Okay, so once we have this now, what we can do is, well, what can we do with this? We can compute the stress matrix by grabbing these Lamé parameters from here, because we're doing plane stress, and insert it here. And also let's grab the actual parameters, these two, and insert them here. And now we can write sigma is equal to 2 times mu plus epsilon times epsilon, sorry, plus lambda times the trace, which is, there's a function built in Matlab called trace of epsilon, times the identity, which is I2. So this becomes the identity here, and there is our sigma. So this is our in terms of newtons per squared millimeter, the Cauchy stress. So this is, both of these are quite unuseful because we have a general state of stress here. So what we want to do is convert this to von Mises, and perhaps if you want to know the strain for any reason, we usually convert this to a equivalent strain measure as well, the von Mises yield criterion. Right, so this works very well if you have a general plane stress state like we have in our case here. It's perfect to use von Mises. And right, so let's compute that. So we have sigma Vm equal to square root, and then we have sigma 1 squared minus sigma 1 times sigma 2 plus sigma 2 squared plus 3 times sigma 1 2 squared. And well, just use sigma 1 2 because they are symmetric. They are quite symmetric here. If we run this, this is our von Mises. You can check this, that, well, we have this value here. Now sigma von Mises is always going to be in absolute terms, so 0.469, so that's like 0.7, and then we have a little bit of strain here and a little bit of y, so this is going to be added on top of this and brings this up a little bit more. So yeah, makes sense. So that's how we do that. Now another thing that is interesting, you can actually write something here. You can say that, okay, von Mises stress. And another type of stress that is very interesting is principal stress. So you can do it by hand, exactly how I showed you, or you can jump into Matlab and do it this way. We have V and D, nope, D, escape, Eig, and sigma. and I get the principal stresses here, and the principal directions here as well. And I believe this is the first and this is the second. Could be wrong. So, and very important thing we need to do here is sort these, because this is always going to be, Matlab is going to give you the lowest value first and then the highest value. But what we want is the absolute value to be the lowest value, or the first value that it spits out. So for us it's very important to sort this by the absolute value. So what I'm going to do here is do diagonal of D. That's going to give me, well, this, and then I'm going to do the absolute value of this. Now I'm doing this, I mean, you just obviously just use this, but I want to be able to change my element here to whatever element I have, let's say 5, and I want this still to be working. Here is no, this still is the highest. Let me see if I can find something that to make my point perfectly clear. Right here, so this is for the third element, and what do we get here? Well, we get the principal stresses minus 0.18 and 0.82. Obviously this stress is larger than this stress. This is just compression, and this is in tension, and this is higher. But if we just choose the first one always and define this as our first principal stress, we won't be getting the maximum stress in the first principle, and that's what we want. We want to define the first principal stress to be the largest stress. So, and if you do that for every element, you will see actually a nice and colorful picture, but if you don't do this, then the picture will be different. I'll get back to what I mean in a second here when we actually plot the stress across the whole element. Anyway, what I want to do is I want to do sort. So I'm going to sort this, and I'm going to grab the second argument of this. And store it in int, so 1 and 2. Sort abs. Is this right? Hold on here. Right, but it should be ascending. So ascending. Okay, what small a? Ascend. Alright, ascend should read the error message. There we go. No, descend. Descend. Now, that's what I want. And I can now say that we have the directions V and this int, I believe, on this side. So we have the first direction here, so this is our original directions, this and this, and now we just take this first. So this is our first direction, this is our second direction, as we can see here, as well as sigma prints is equal to well, diag of it's not gonna work. Yeah, I'm gonna do this in 2 steps. So I'm going to do sigma prints equal to diag d. I can use this in here, and I can do sigma prints is equal to sigma prints end. There we go. So this is my sigma principle before reordering, and this is my sigma principle after reordering. Right. Now, what I can do as well is to plot these directions. So I'm just going to quite fast here do the midpoints, IP, and we have, well, we can do mean of IP in the one direction. That's gonna give me this. This is the midpoint, X and Y. And I can do a quiver in the XM1 and XM2, so this is my X and Y point, and then our direction is going to be dir dir 1 1, that's the first component, and dir 1 2 1 is our second component. This is blue, and I want to do hold on here, hold on. So I'm gonna plot this on top of my midpoint for the original element anyways. Yeah, so this is my stress in the first component, in the principal direction, and this is in the second, so I'm gonna do this red, and this second one is in the second column, so I'm just gonna switch this to 2 here and rerun it, and there we go. So here is where the most stress is, and here is where the least stress is. So if you look at the sigma principle, this is the amount of stress going in this direction here, and this is the amount of stress going in this direction here. So we have tension across this way, and we have compression across this way. And in fact, if I get rid of this compute stress and strains, if I get rid of this figure here, then all of this stuff is going to be, and if I do F5 now, all of this stuff will be drawn on top of my original element here, and I can zoom in to this region. I can see there is my element, my original element and my deformed element. So my original element has this strain here, and it sort of makes sense, right? This whole thing is indeed in tension on this side, and there is very little compression happening to this side here. There's a little bit, but it's quite little. So this puts everything in a bigger frame. Right. Alright, so that's how we compute the stress and strain for one element. And yeah, so you should be able to do this. You should definitely be able to do this by hand, and if not in Matlab as well, because I'm going to ask you for higher credit to do this for every element. And in the next video we will see how to do that and how to do nodal averaging as well.